All right, thank you, Corey. So I have been an assistant professor at the University of Delaware for the past year and a half, and my lab is really interested in root systems, particularly in corn. So I'm going to give you kind of a broad overview of roots, and then specifically we're going to talk about brace roots, and that, again, is where my lab focuses. So it should come as no surprise to any of you that roots are critical for plant health and productivity. They play a role in anchorage and stability. We'll come back to this in how brace roots contribute to this, specifically in corn. They also have symbiosis. So this is an example of a nodulation in legumes. This is not necessarily happening in corn, but there's other symbiotic relationships that contribute to root health. And also, they're important for our soil resource acquisition. So our water, our nitrogen, and our phosphorus are all coming from the root system. Now, the arrangement of roots within the soil is called the root system architecture. And this is basically how the arrangement of the roots within the soil dictates how much of different resources that they can acquire from the soil. So I've done two kind of extreme examples here. One is a root system that's really narrow and deep. The other is a root system that's wide and shallow. And so each of these has been proposed to be important for different types of resource acquisition. So under phosphorus limited conditions, which of course is not necessarily a problem here in the Delmarva, we would have a shallow root system would perform better because the phosphorus sits in that topsoil and the shallow root systems can extract it. In contrast, under water limiting conditions, a deeper root system performs better because it can access those deep water resources within the soil. So corn and other cereals have what's known as a fibrous root system. This is a side view of a corn plant where the soil has been removed from the root system, so you can see some of the roots in this. If we were to take then a cross section through the stalk, what you see is these roots are arranged around nodes of the stalk. So on the very bottom, we have our first four nodes that are compressed right at the base of the stalk. We then have a fifth node of roots that is still under the soil surface. A sixth node of roots appears right at or above the soil surface. And then a seventh node will often appear as well with what are known as brace roots. So for the purpose of our talk, the whorls of the sixth node and the seventh node are going to be called brace roots because they're rising above the soil surface. So I'm a basic researcher who is interested in taking that basic research to application. And when we think about root systems, they're incredibly challenging to study. So they're under the soil. How do we study them? And when we think about studying roots, we really think about three important metrics. One is the accuracy of our measurements. The other is the environment in which those plants are grown. And the last is the throughput. Can we measure one plant? Can we measure 100 plants in the same amount of time? And so on this kind of peak between accuracy and environment, we have a lot of medical imaging technologies that have been used to look at root systems in soil. So an MRI, magnetic resonance imaging, or an X-ray CT are able to distinguish roots within soil. The problem is that this is done in greenhouses. So right now, we don't have a way to take these medical imaging technologies out into the field and image roots within the field. There's ongoing work to develop a field-based X-ray CT scanner, but there hasn't met with much success yet. On the other kind of part of this triangle, we have things that are really good for the environment. Manual excavation, which is where we'll focus a lot of our attention today, which is basically digging up and cleaning your root systems. So this is ideal for environment because you're actually in the field where that plant is growing and it's encountering all of the different soil environments. We also have what are known as automated rhizotrons. So these are just clear glass boxes where you can grow roots in soil. And then we have a completely artificial environment, which is known as gel imaging. So you basically can grow plants in a clear gel and you can quantify the root system. So this is great for accuracy. You can get incredibly accurate measures of root systems, but what growth in a gel has to do with growth in a field? Very little, right? So we're going to focus, for the purposes of this presentation, on these roots we've seen by manual excavation. So when we think about root systems and these fibrous root systems, there's really two classes of root system within there. The first is the seminal root system, which comes from the embryo and the seed. So you may have heard this referred to as the primary root system. This is kind of a misnomer. It's primary in the fact that it's the first root system that appears for the plant, but it is not primary in the fact that it is the major contributor to plant health. So the seminal root system, again, originates from the seed. So coming here in this series of germinating seeds, this coming out the bottom is what's known as the radicle or the primary root. This is the first root of the plant and the first root of the seminal root system. We then get additional seminal roots from the seed, from the scutellar node that appear. And this is all happening prior to emergence and around emergence. Now, the second root system is what's known as the nodal root system, and this is the most important root system for the plant for the majority of its life. So it initiates around the V1 stage, and by V6 is the main root system of the plant and will continue to be for the life of the plant. So these are the roots that come from those nodes. If you remember, I showed you that cross-section of the stalk. That is those nodal roots coming out of nodes. So here is the very first one coming out of this node here. And that leads to this entire root system of different nodal roots with lateral roots coming off of it. So researchers have proposed an ideal root system, right? What does a root system architecture look like in corn that would be optimal for corn productivity? And basically the model that they proposed is what's called steep, cheap, and deep. And their proposal is that if you get really steep root angles and you send your roots really deep, that you can still explore the upper soil layers by lateral branching, but you really ensure that you're exploring those deep resources of the soil. Full confession, there's not a lot of proof that this is good, right? This is just purely intellectual proposition that this is probably going to be good for the plant. One of the things we'll come back to is the primary roots or the seminal roots should be cold tolerant. So we'll talk about why that's important in a couple slides. And one of the caveats to this is that they want all these roots to be unresponsive to nitrogen or other soil resources. So they basically are proposing that you establish a root system and that is not responding to the environment. The challenge to this, of course, is that roots are not static. They're dynamic, and they're constantly responding to the availability of different nutrients, to different stresses, and there are multiple factors affecting root architecture, which is, first of all, the genotype of the plant you're working with, right? So what hybrid are you using is going to affect your root system architecture. Then, based on the developmental stage of your plant and the type of stress you're experiencing, you're going to see differences in the root. So first, what kind of stresses affect seminal roots? So this diagram here is basically the different growth stages of corn and the predicted yield losses due to stress. So you can see that if you have a stress kind of early, it's not predicted to have a major effect, but in these middle stages, the stresses have a much greater impact. And part of this is due to damage to the roots themselves. So what stresses affect seminal roots? If you remember, seminal roots are those roots that are establishing before emergence. And if you're not getting seminal roots, you're really going to reduce your uniform emergence. You may not have emergence at all. The major factors that influence this are, of course, cold temperatures. So conservatively, if you have temperatures below 50 degrees Fahrenheit, this is going to damage your root system. You can likely recover as a plant from temperatures below 50 degrees, but if you're below 28 degrees, this is lethal cold and the plant is not going to survive it. The other major stress that can affect the seminal root system is salt injury. So if fertilizer is applied too close to the seeds, the root tips will burn. You'll see like blackened or browned root tips, and you can, again, delay emergence or inhibit emergence completely. The question of whether you delay or inhibit depends on if those nodal roots are ready to form or not. So if the nodal roots are there and they can come out and take over for the seminal root system, you'll likely just see a delay in emergence instead of a lack of emergence. So what about the nodal roots, right? These seminal root systems are only around for a small amount of time. Even though they're the first roots that are coming out, they're not playing a significant role in the root system of the plant. So what stresses affect the nodal roots? And if we look very early, a big thing that we see is what's called floppy or rootless corn. And so this is a symptom of very dry topsoil. So this here, you see this cracked topsoil, this plant is kind of flopped over, called rootless. Basically what happens is, if you were to excavate this plant, you see that you have a really nice seminal root system here. You have an intact mesocotyl, but now your nodal roots are desiccated and not forming. So if we zoom in, this is the desiccated nodal roots. You can see these root tips that have just dried out. So this is, again, a lack of moisture. If you plant too shallow, a lot of times this is what happens. And without those nodal root systems, the plant won't stay upright, it won't establish, and your plant will fall over. So this is one of the earliest stresses that can really dramatically affect the nodal root system establishment within the soil. And now if we look kind of throughout the life of the plant, we see differences from the type of soil, the soil density, and how that impacts the root system. In this case, looking at root length. So on the left, we have roots that are grown in liquid, roots that are grown in fog, sand, and the field environment. And you can see these massive differences in root length in these different environments. And it corresponds to the density of the material. So if a root is trying to penetrate really compacted soil, right? If you have soil compaction, you'll have a limited root system. Your root is not going to be able to grow deep, which if you remember was one of the ideal things about our root systems is that they can grow deep to access those deep water resources. And so root length is kind of inversely correlated with the density of the material you're growing in. We also see that nutrient availability stresses. Roots respond to that. So often what you're seeing above ground, in this case low nitrogen versus high nitrogen, right? Your plant, you see that in the foliar part of the plant, but there are also responses happening below the soil. Particularly in low nitrogen, the root systems are trying to find nitrogen. So they're investing their resources to growing their root system to find nitrogen. And again, with phosphorus, there are some genotypes. So this response depends on what plant you're using as well. So some of these plants are efficient at using phosphorus and some are inefficient. If you have enough phosphorus in your soil, it doesn't matter how good the plant is at acquiring the phosphorus. You get the same root system. But if you're in a phosphorus limiting situation, now you see that a phosphorus efficient plant can make a lot more roots to pull the phosphorus out of the soil than a phosphorus inefficient plant. So the takeaway here is that different soil stresses have different impacts on the root system. But because of our challenges in studying root systems, we don't understand these very well. And basically, stresses have been studied in isolation. So I take a root system and I've done a nitrogen stress, and I'm looking at how the roots respond. I've done a phosphorus stress, I've done a water stress. But a plant actually experiences multiple stresses, and we don't understand how root systems respond when they receive multiple cues. How do they decide what they respond to? And these cues, of course, are nutrient availability, water availability, the soil properties, which we talked about. Pore size is going to impact not only the ability of the soil to hold water, but then also how the root system penetrates into the soil. One of the things we haven't even talked about are insects and microbes. So if we have corn rootworm damage, the plant has to decide how to respond to that. And then the neighboring plants. So we still don't understand a lot about root systems, mainly because they've been incredibly difficult to study based on the fact that they're underground. So there's a lot of work to try to understand how a plant and how a root responds to competing signals. If I have enough water, but I don't have enough nitrogen, or maybe I have multiple stresses, how do I respond to those? So I want to switch gears a little bit to talk about neighboring plants. So another major impact on root systems is planting density. So you know that we've increased our yields in the US by increasing planting densities. But with that increase in planting densities, we're also reducing our root systems. So this is just one experiment so I converted, they had plants per hectare up here, and I converted it into plants per acre on the bottom. So about 16,000 plants per acre, 28,000, 34,000 plants per acre. You can see that these root systems are dramatically changing as you increase the density of plants. This is likely, we don't quite understand this, but we think it's because they're competing with their neighbors for resources, and they're keeping, they're kind of setting their fences and keeping their neighbors out. And when you have more plants packed together, those root systems can't expand as much. Coming along with this reduced root system is increased lodging, right? So this is another example where they've planted at different densities. So in this blue circle are about 18,000 plants per acre, and they're looking at their yield versus lodging. And at this low density, you have very little lodging and medium yields. And as you increase your density, you see an increase in yield. But now when you hit this highest density in red of 36,000 plants, you can see that we have a massive drop-off in yield. And this massive drop-off in yield is due to this increased incidence of lodging. And it's thought that this is due to the establishment of the root systems, right? You're not getting enough root in the soil to establish a stable plant. So, of course, lodging is very difficult to assess what the impact would have been because you don't have a nice control field that stayed upright that would tell you what your yields would have been if your field hadn't lodged. So one group in the late 80s tried to do this by manually lodging corn plants. So they basically had a cornfield, and at different stages, they knocked the plants to the ground, and they asked, how does that impact my yield and the plants themselves? So on the left, you see a control plant. The next one over is a plant that has been knocked over at the vegetative 10 stage, V10. And you can see there's a little curve in the bottom of the stalk, but it's minimal. And that corresponds with very minimal yield losses. So 3 to 4% if you have a root lodging event from V10 to V12. Of course, these are, 30 years ago crops, right? So we don't really know how this translates to today. If they lodged a V13 plant, you can see now there's a larger gooseneck, V17, even larger gooseneck. And these correspond with increasing yield loss. So if they lodged after V17, they saw 15 to 25% yield losses from root lodging. And if you've ever tried to combine a field that has lodging, you understand why this happens, right? The lodging events, even if they come back up, they really prevent your combine heads from getting in and harvesting the grain. So what can we do about lodging in late stages? And this is where we come to this last class of nodal root called the brace root. So brace roots are named because they're thought to brace plants and provide stability and lodging resistance. And so the question my lab asks is A, what are brace roots there for? Do they contribute to stability? So what is the purpose of these brace roots? Do we need them? Are they a waste of carbon for the plant? And so I want to first say that if you read the literature, or if you've talked to a farmer, or if you are a farmer, everyone has their own opinion about what brace roots are good for. There is no research that tells us what brace roots do. So again, stability is the obvious choice. They're called brace roots. They look like they brace the plant, but we don't know this. It has not been tested. The other thing that they are proposed to be important for is late-stage nutrient and water acquisition. So some people propose that they are not there for stability, but they are roots that come out later and they're still actively growing and able to acquire resources from the soil. Others say that brace roots are a bypass for a damaged underground root system, and that they only appear if the underground root system can't get what it needs. And if you've heard of others or you have other opinions, I would love to hear them. Basically, we want to test each of these theories to understand what brace roots do for a plant. So the first one that we tested was stability. And brace roots are proposed to have two different roles. So the one that we're testing is this one on the left, which is that they provide stability to prevent lodging. And they actually keep the plant more stable. The second thing they do is after a lodging event, the brace roots grow out the length of the stem and actually keep the stalk off the ground. Some people have said that they think the brace roots will actually push the stalk back upright. This phenomenon on the right, giving away my punchline. This phenomenon on the right, we know nothing about. We know nothing about how these brace roots form in response to lodging, whether they actually help or not. So what we have been focusing on now is this first question. Do they provide stability to prevent lodging? And the way that we are doing this is with these field-based devices that allow us to apply a force and measure the rotation of the device. So this is one of my PhD students, Lindsay, who is demonstrating this device. So I'll go through a little bit more detail about how this device works. But basically what we can do is we can flex test, so this is what we're calling flex testing, the stalk. We can then cut off the 7th node of brace roots. We can flex again. We can then cut off the 6th node of brace roots and flex again. And look at how the flex strength of that stalk changes as we lose brace roots. So the reason why this works is this is a standard graph of mechanical testing. So plant materials all behave approximately the same. Basically, when you're testing a material, you're applying a force and you're looking at how much displacement that object has with those increasing force. So here we have our increasing force, and here we're looking at displacement. So there is this range here, which is called the elastic range. This is, you can imagine just a rubber band, right? You pull a rubber band out and it returns back to its original form. So this plant materials have an elastic range where you've not permanently changed them. And that is the range we're measuring in. We then, as an object, it sees the highest load it can take, and then you have what's called plastic deformation. This is deformation that is not going to go back. This is a permanent change to that object. And then you have failure of the object. So we, as I said, we are working in the elastic range, which is why this works. So we can measure the stiffness of this material, which is basically the slope of the elastic region of a mechanical testing curve. So what this looks like on the device itself is these bananas. So what we're seeing on this axis is the load, and you're seeing the rotation on the bottom here. So this curve is, as we apply the force, we're measuring the rotation. This bottom part of the banana is as we come back upright. And we repeat this 3 times. This proves that it is elastic because you see the same curve every time. That means we haven't permanently changed the material itself. Okay, so what do we see? If we cut off brace roots, what happens? We see dramatic differences in stiffness of the stalk. So here, this is 15 different plants of the same genotype. We have a relative stiffness, so this is our completely intact plant. We've normalized it to 1. If we removed just that uppermost node of brace roots, we see about a 15 to 18% reduction in stiffness. And now when we remove both 7 and 6, so remember 6 is that node that's right on the soil surface, we see that we go from 1 to around 0.4. So that means 60% of the stalk stiffness is due to the presence of brace roots. So what we're working on now is understanding what about brace roots does this. Are all brace roots created equal? Right? As I said, that graph we got from this field season, it was a single genotype. Are there differences between genotypes? And what about brace roots makes them good at stabilizing? So I've shown you here 3 different pictures of brace roots. So on the far left, you see one where the brace roots kind of track the soil surface before they penetrate into the soil. In the middle are ones that penetrate immediately. And on the right, we have ones that also penetrate immediately but are a lot thinner, right? Does any of this impact the ability of a brace root to stabilize a plant? So what we're doing to answer this question is we have 55 different inbred lines. Because this was so successful the first year, we've decided that next year we're also going to test some hybrids. Hopefully we can coordinate with some variety trials in Maryland and Delaware to actually look at the brace roots in those specific varieties. But for now, we've been really focused on research inbred lines. We can then manually excavate the root systems, clean them off, and dissect off the brace roots. We can use image analysis to pull out information about these brace roots. One of the other interesting things about brace roots as a root type is that they usually don't branch until they hit the soil surface. So in this image on the right, you can see which of those roots has penetrated the soil based on the fact that they start to branch. We see differences between genotypes in how much of this branching. And that may play a critical role in stability, because if you don't branch a lot, you're not anchoring to the soil as well. But we're trying to, this of course is terminal. Once you dig up a plant, it's done. So what we're trying to do is get more dynamic information. And we're doing this by building robotics. So we have built a ground-based robot that will run through under the canopy and take pictures from the side of the brace roots throughout the growing season. So this is the latest version of this. We've had one version that was a disaster. It was designed by a mechanical engineer to work in a lab and not a field. And of course, fields are very dynamic places. So the second version has tank-like tires and is much better at navigating the field. And basically what we can do is we can mount different imaging systems on the top of this. If any of you were in Jared Miller's talk, these are the same types of imaging that he is deploying on his drones. And we can basically get images of the stalks with the brace roots and quantify throughout the growing season what's happening. The other aspect that we are thinking about is when we think about what makes brace roots good at stabilizing, there's one really important thing about brace roots that we can't ignore, and that is that the cell walls of brace roots above ground are reinforced. So this, again, is work from the 80s. This is a cross-section of a single brace root from the part that's above ground and the part that's below ground. And the part that is above ground has these really thick cell walls. It's thought that this is because they need to stabilize the plant. And so we wanted to understand how the thickness of the cell wall relates to the mechanical properties of the root itself. So we're also doing mechanical testing, not just in the field with these flex tests, but we can now take brace roots and do mechanical testing as if they were any material, and we can look at how their strength changes. And we're already seeing differences between genotypes. So if we look here at stiffness, this is from, this would be World 2, which is basically node 7. And we see that these two are approximately the same, and this one has much higher stiffness. So what we want to do now is take this information and ask how it relates to how well these brace roots stabilized the plant. The other thing I wanted to touch on is this late stage nutrient and water acquisition. So they're still roots, right? What do they do for the plant that's maybe not stability? And the reason this has been proposed is because if you look at here the growth stages of maize and where their water and nutrient demands are highest, it occurs at the time when the node 6 brace roots have reached the soil and are continuing to be active roots. And so people have proposed that because this is the most critical time for water and nutrient acquisition, that maybe the most important thing that brace roots do is acquire water and nutrients and respond during those time frames. This is supported by the fact that brace roots have immense capacity to move water and nutrients. So if you remember, xylem elements are the kind of pipes that move water and nutrients from the soil up into the shoot of the plant. And if we look here at a cross section, this is the primary root. These big holes are the xylem elements. So a primary root has approximately 6 of these tubes. This is the second nodal root. It now has about 16. The 5th nodal root down here has about 18. And now when you get up to the 7th nodal root, which is going to be a brace root, these have 33 or more. So in our experience, they have much more. So this is basically, if you think about it, it's a plumbing problem. If the more pipes you have, the more ability you have to move water. And this has been why brace roots are proposed to be really important for that late stage nutrient and water acquisition. So basically what we're doing now, ongoing work in my lab, is continuing to understand how they contribute to stability. What is it about brace roots that make them good at stabilizing a plant? And then we want to understand what is their capacity for nutrient and water uptake? Is the fact that they have more metaxylem elements relevant? Maybe if the soil resources aren't there, it doesn't matter how much capacity they have if they don't do it. And then we want to understand, is there a trade-off between these two? If you're really good at being a stabilizing root, do you compromise your ability to uptake water and nutrients? And how do we find kind of a middle ground where you're pretty good at both? And then lastly, the big picture question that we're working on is, what can this above ground root system tell us about the health of the underground root system? So one of our major challenges in understanding roots has been the accessibility. So if we understand how above ground roots respond to what's happening below ground, we could use that above ground root system as a proxy for underground root health, right? So if I have extra nodes of brace roots appearing, does that mean my underground root system is stressed and it tells us that there's maybe something wrong with that plant? So that's where we're headed. That's what we're really interested in asking, those types of questions. So lastly, I want to talk about what is the best way to evaluate root systems. And unfortunately, it remains to be digging up a plant and cleaning the root system off, right? This is, of course, terminal. So if you diagnose a plant, you can't treat that plant. Technology just isn't there yet where we could do live diagnostics of root systems. But I will say that one of the things that we have improved this year is that instead of cleaning with hoses, we're using an air compressor with a nozzle attachment to blow the dirt off the root system. And this works beautifully for maize root systems. It cleans them very fast, very efficiently. And the maize roots are so sturdy that you're not breaking apart your root systems. This wouldn't work as well for other plants. So with that, I'm happy to take questions, and I already have one.